On July 14th, 2015, a spacecraft the size of a grand piano flew past a small, icy world at the edge of the solar system and sent back the first close-up photographs anyone had ever seen of it. Mountains made of water ice, a heart-shaped plain of frozen nitrogen, an atmosphere so thin it was barely there at all, backlit by the sun in a photograph that made an entire generation of scientists stop and stare. That spacecraft was New Horizons. That world was Pluto. And for a few weeks in the summer of 2015, it felt like the beginning of something. The opening chapter of a new era of outer solar system exploration. There's a strange irony sitting underneath that moment, too. New Horizons had launched in January 2006, back when Pluto was still officially classified as the solar system's ninth planet. By the time the spacecraft actually arrived, 9.5 years later, the International Astronomical Union had already reclassified Pluto as a dwarf planet. A decision made in August 2006, just months after launch. The world New Horizons was racing toward changed its official status while the spacecraft was still in flight. 11 years later, nothing has followed it. No orbiter, no lander, no second mission has ever been sent back. And the reasons why aren't simple, and they aren't accidental. They come down to distance, radioactive fuel, billions of dollars, and a set of scientific priorities that quietly placed Pluto behind several other worlds in line. Tonight, we're going to walk through exactly why NASA hasn't gone back, what it would actually take to change that, and why the answer isn't a lack of interest. It's a lack of almost everything else a mission like that would require. Let's start with the flyby itself, because it explains almost everything that came after it. New Horizons launched on January 19th, 2006, and spent 9.5 years crossing the solar system before it ever reached Pluto. Even moving at roughly 36,000 miles an hour, fast enough to cross the distance from New York to Los Angeles in about 4 minutes. It still took nearly a decade to get there. Pluto orbits, on average, about 3.7 billion miles from the Sun. That's not a distance you cover quickly, no matter how fast your spacecraft moves. And because New Horizons was built for a flyby, not an orbit, it only had one shot. It sped past Pluto at more than 30,000 miles an hour, gathering as much data as its instruments could capture in a matter of hours before continuing on into the Kuiper Belt, where it eventually flew past a small object called Arrokoth in January 2019. It's still out there today, still transmitting, still doing science on the solar system's outer frontier, but it can never go back. It doesn't have the fuel, and its trajectory only ever pointed one way, outward. That single fact is the root of the entire problem. Everything humanity currently knows about Pluto up close came from a spacecraft that saw it once for a few hours and then kept flying. If you want more than that, if you want months or years of observation, mapping, and orbit-based science, you don't send a flyby probe, you send an orbiter. And an orbiter to Pluto is a completely different and vastly more difficult kind of mission. Here's why. To orbit Pluto, a spacecraft has to slow itself down enough to be captured by the gravity of a dwarf planet that has only about 0.2% of Earth's mass. That takes an enormous amount of propellant, which means an enormous amount of extra mass on the spacecraft, which means a much bigger and more expensive rocket to launch it in the first place. Engineers who've studied the concept, including a mission design known as Persephone, discussed by planetary scientists in 2025, have estimated that an orbiter, capable of circling Pluto for 2 to 3 years, mapping its surface and studying its atmosphere in detail, would weigh nearly 5 times what New Horizons weighed, largely because of the fuel needed just to break into orbit. One version of that concept has a genuinely elegant twist to it. After completing its orbital tour of Pluto, the spacecraft would use a final pair of close gravity assist flybys of Pluto's largest moon, Charon, to fling itself free of the Pluto system without burning any additional propellant, then continue on using an ion propulsion system to tour several more Kuiper Belt objects, and possibly even settle into orbit around a second dwarf planet entirely. It's an ambitious, multi-stage mission profile, but every stage of it depends on getting that much mass safely into orbit around Pluto in the first place, which is precisely the expensive part. And weight isn't the only problem. Power is arguably the bigger one. At Pluto's distance, sunlight is roughly 1,000 times weaker than it is here on Earth. Solar panels, the kind that power missions closer to the sun, simply don't work out there. Every spacecraft that has ever operated in the outer solar system, Voyager, Cassini, New Horizons, all of it, has relied on something called a radioisotope thermoelectric generator, or RTG, a device that converts the heat released by decaying plutonium-238 directly into electricity. And that's where the second major obstacle comes in, one that has almost nothing to do with Pluto itself and everything to do with a fuel shortage back here on Earth. The United States stopped producing plutonium-238 domestically in the late 1980s, after the reactor that made it at the Savannah River site in South Carolina was shut down. For years afterward, NASA relied on leftover stockpiles and limited purchases from Russia to power its missions. Domestic. Production restarted at Oak Ridge National Laboratory a little over a decade ago, but it's a slow, expensive process. Current production sits at roughly 1.5 kilograms a year, and the last Planetary Science Decadal survey specifically recommended increasing that rate to support future missions, a recommendation that, as of this year, still hasn't been fully funded. Every mission that needs an RTG is competing for a share of that limited supply. Right now, that includes Dragonfly, NASA's rotorcraft mission heading to Saturn's moon Titan, and a future flagship mission to Uranus that the last Decadal survey ranked as the highest priority. New outer planet mission for this decade, ahead of a Pluto orbiter. Every kilogram of plutonium committed to one mission is a kilogram that isn't available for another. A Pluto orbiter needs it. So does everything else out there, and there simply isn't enough to go around for all of them at once. To put the scarcity in perspective, NASA's own Inspector General has warned that even hitting the current production target of roughly 1.5 kilograms a year carries risk, and the agency has acknowledged it would need to lean on the Department of Energy to increase production if mission demand grows beyond what's already planned. A single RTG for a mission like Dragonfly requires several kilograms of plutonium oxide on its own. At that rate, building up enough surplus fuel to comfortably support a Pluto orbiter on top of everything already committed isn't a matter of months. It's a matter of years, possibly a decade or more of steady production before the stockpile problem stops being a limiting factor at all. Which brings us to the third obstacle, and it's the one that ultimately decides everything else: money and where NASA is currently allowed to spend it. An orbiter mission to Pluto, by recent engineering estimates, would cost somewhere in the range of $3 to $5 billion, spread out over a mission that could easily take 15 to 20 years from approval to arrival, once you account for design, construction, the long cruise phase, and the orbital tour itself. That's an enormous, multi-decade commitment. And right now, NASA's planetary science budget is under more pressure than it has been in years. In 2025 and 2026, NASA's science programs faced repeated proposals for historic budget cuts. In one case, a proposed reduction of nearly half of the entire science budget in a single year. Congress ultimately restored most of that funding, but the fight over it has left planetary science with less room to start expensive new flagship missions, and it has pushed agency priorities toward missions already deep in development, like Europa Clipper, which is already on its way to Jupiter's icy moon, and Dragonfly, which is scheduled to launch toward Titan later this decade. Pluto, for now, has no mission in active development at all. The Persephone orbiter concept exists as a serious engineering study, discussed by scientists and reviewed for the most recent Decadal survey process, but it has not been selected, funded, or given a launch date. It remains at this point an idea on paper, a genuinely exciting one, but one competing against Venus missions, Mars sample return efforts, ocean world missions to Europa and Titan, and a Uranus flagship that the scientific community has ranked as the more urgent priority. So when people ask why NASA doesn't care about Pluto anymore, that's not really what's happening. The truth is closer to the opposite. Scientists working on Persephone and similar proposals are visibly excited about it. The problem isn't enthusiasm, it's that a Pluto orbiter sits at the expensive, technically difficult end of a very long list of ambitious missions, all competing for the same limited pool of money, launch vehicles, and radioactive fuel, in an agency currently fighting simply to keep its existing missions funded. There is a version of this story with a faster ending, and it's worth mentioning because it shows how differently this could play out if the constraints changed. Some proposals, including a NASA-funded concept using an experimental fusion-based propulsion system called direct fusion drive, have suggested that with a sufficiently advanced engine, a Pluto orbiter and lander could theoretically reach the dwarf planet in as little as 4 years, instead of the decade or more a conventional mission would require, while delivering far more mass than New Horizons ever carried. That technology, though, is still in early experimental development, tested in small-scale laboratory conditions, not built, launched, or anywhere close to ready for a real mission. So here's where that leaves things, honestly. Pluto isn't being ignored because scientists lost interest after 2015. If anything, New Horizons made Pluto more interesting than anyone expected. It revealed towering mountains of water ice up to several kilometers tall, a vast plain of frozen nitrogen and carbon monoxide informally named Sputnik Planitia that shows signs of being geologically active today, hints of ancient liquid water that may have once existed beneath the surface, evidence suggesting a subsurface ocean could still exist right now in a thin, layered nitrogen atmosphere that continues to surprise researchers analyzing the data years later. Every one of those discoveries raised new questions that only a longer, closer mission could ever answer. but answering them requires slowing down enough to orbit a small, distant world with almost no gravity to help you, using fuel that America has only recently started producing again in meaningful quantities. Funded by a budget that is currently strained across dozens of competing priorities, the scientific community has ranked as more urgent. None of those are excuses. They're the actual unglamorous mechanics of why a second Pluto mission hasn't happened yet, and why, if one does happen, it's more likely to arrive in the late 2030s or 2040s than anytime soon. New Horizons gave humanity one perfect look at Pluto, gathered in the space of about a day after a 9.5-year journey to get there. Everything since then has been proposals, studies, and waiting, not because nobody wants to go back, but because going back is one of the hardest and most expensive things NASA could choose to do in a decade where it's already being asked to do almost everything else with less. It's a genuinely strange position for a space agency to be in. The excitement is real, the science case is strong, and the mission concepts already exist on paper. And what's missing is the years of steady, uninterrupted funding and fuel production it would take to actually turn any of them into a launch date. If you want to know the moment a real Pluto orbiter mission finally gets approved and funded, subscribe and turn on notifications, because when it happens, it won't be quiet, and you'll want to be watching when it does.